Hi, this is Mrs. Hogan. In this video, I'm going to go over simple machine, wheel and axle. In the wheel and axle simple machine, the wheel is just considered a lever arm that is fixed to a shaft, and that shaft is called the axle. Then, the wheel and axle move together as a simple lever to lift or to move an item by rolling. And here are a few good examples of the wheel and axle. When finding the mechanical advantage for a wheel and axle, it is important to know within the wheel and axle system which is applying the effort and resistance force, the wheel or the axle. For a larger mechanical advantage, you would want to put your resistance force here on the axle. That output distance is going to be smaller. So that means with the larger distance on my wheel, I'm going to require less force to move this resistance force. If I put the resistance force, or that output, on the wheel, then the distance is greater here than it is where my effort force, or that input distance, is going to be. So my mechanical advantage is going to be less than 1 when I'm using the wheel and axle, where I have the resistance force on the wheel, my effort on the axle, and it's going to be greater than 1 if I have my resistance on the axle and my effort on the wheel. To find the ideal mechanical advantage for a wheel and axle, it's going to be found the same way as you've been doing the other simple machine ideal mechanical advantages. We're looking at our distance effort over distance resistance. With the wheel and the axle, both your effort and your resistance forces are going to travel in a circular direction. Right? And they're also attached to each other, so they're going to be traveling at the same speed. The distance that each one of these travels is going to be their circumference. Remember, circumference is either 2 pi r or pi d. So when I'm trying to find my distance effort and my distance resistance, first I have to know where is my resistance attached, the axle or the wheel. Well, my resistance in this picture here is going to be attached to the axle. So because it's attached to the axle, my dr is going to be that pi times the diameter of my resistance, which is the diameter of my axle here. And my distance of my effort is going to be the wheel, because that's where my effort is going to be put on. And so it would be pi times the diameter of the wheel, if I was using this as my example. Now notice for IMA, my distance of my effort and distance resistance both have pi in them. Well, once I have written this out, I can actually cancel both my pi's because it's going to be on top and on bottom. So now it becomes IMA is just your distance of your effort, the diameter of the effort, divided by the diameter of that resistance. Like I said, in this case, the axle diameter and the wheel diameter. So let's go ahead and look at this example here. It says, what is the IMA of the wheel above if the axle is driving the wheel? So that means if my axle is driving, that is where I'm putting my effort. So my distance effort is going to be, if I look up here, it tells me it is the diameter, that's what this symbol right here means, is 6 inches. It's a diameter, like we learned before, you cancel out your pi's. So I'm going to put 6 inches. Then my distance of my resistance is going to be my wheel in this case, because the axle is driving the wheel, which means that the wheel is my resistance. It's where my resistance force is. And it tells me with this symbol here that the diameter is 20 inches. They're both in inches, so inches is going to cancel out and give me 0.3. Okay, so what happens if I have the wheel driving the axle? Well, if the wheel is driving the axle, that means my effort force is going to be on the outside of the wheel. And so that means my distance effort on top this time is going to be 20 inches. And the diameter of my axle, because it says the wheel is driving the axle, so my distance of my resistance this time is going to be 6 inches. So 20 inches divided by 6 inches, inches canceling out, equals 3.33. Again, I'm consistent with my diameters. I don't have a radius and a diameter. I made sure they were both diameters. Now you can see that if I have the resistance force on my axle and my effort force on the wheel, my mechanical advantage is going to be greater than 1, this 3.33, because the distance where my effort is greater. Now, of course, if I put the resistance force here on the wheel, where the greater distance is, notice it's less than 1. So I don't actually have a mechanical advantage in that case. When I'm looking at the 3.3 here, this tells me that it takes 3.3 times around for the wheel for the axle to go the same distance as the circumference of this wheel. And then if you look at this 0.3, then we know that for the wheel to go the same distance as the axle, it only takes 0.3. So I just moved the wheel about a third, and I have went the same distance as it is around for the axle. Just like all the simple machines you've done so far, whenever we're finding the actual mechanical advantage for a wheel and axle, it is the same. My actual mechanical advantage is equal to my force resistance divided by my force effort. Looking at this same example that you just did for your IMA, now we're looking at the AMA. So what is the AMA if the wheel is driving the axle? All right, so again, wheel is driving the axle. So that means that I'm going to put my effort force on the outside of the wheel. So effort is going to be 70 pounds. And my resistance, again, wheel driving the axle, that means my resistance force is put on the axle, and it tells me it is 200 pounds. So force resistance, 200 pounds, divided by force effort, 70 pounds. Pounds canceling out, leaving me with 2.86. So, what is the efficiency for this wheel and axle example? So, percent efficiency equals AMA divided by IMA times 100, and that is going to be equal to my AMA, which I found on this slide, which is 2.86, and the IMA that I found for the wheel driving the axle on the slide before is 3.33. So 2.86 divided by 3.33 times 100 is going to give you 85.9%. All right, here's another wheel and axle example. So I'm going to be finding distance of my effort. I'll also be finding distance of my resistance. I'll need the force of the effort and force of the resistance for this problem. Alright, so my distance of my effort is going to be where the effort is put, and I know that it's going to be on the rim of the wheel. So it tells me here that the wheel is 3 feet. Let's say 3 feet. My distance of my resistance then is going to be the axle, which is 6 inches. I'm going to go ahead and convert that to feet now. Alright, so my force of my effort is what I'm trying to find out. And it tells me that I'm lifting a force of 75 pounds for 20 feet. Alright, so we're going to assume here that AMA equals IMA. Sometimes we have to assume that to solve our math. So I know then that my force of my resistance, which is 75 pounds, divided by X, equals my distance of my effort, which is 3 foot, over 0.5 feet. All right, so we look at this 20 feet. Do I need to actually put this 20 feet into my equation? All right, so my IMA turns into a ratio. All right, so 3 feet divided by 0.5 feet is going to give me 6. So that means that there's a ratio of a 6 to 1. So my wheel is going to go around 6 times before my axle has moved the same distance as 1 time for the circumference of that wheel. So my ratio isn't going to change. It really doesn't matter if I'm looking at 20 feet because we're still looking at that same ratio of this 6 IMA. So all I have to do is just plug it into AMA equals IMA, and really this is just some extra information that I don't have to use. All right, so then I say 75 pounds times 0.5, and then divided by 3 feet. Right, my feet are going to be canceling out, and I will have 12.5 pounds. All right, so now it's time to see what I can find in the kitchen. In the kitchen here is another great example of a simple machine. We're looking at the wheel and axle. In this one, I'm going to be looking at this knob. The knob itself is your wheel. Right, so if I turn, I can turn it on easily. But if I take it off, we're looking just at the axle, and I try to turn just the axle, it's very difficult, and I actually cannot get it to turn on. If you've ever had one of these break off, a lot of times people will go and get some pliers to be able to turn it on. Again, we're increasing our mechanical advantage by doing that. Right? So now, whenever we're looking at our ideal mechanical advantage, let's start by measuring the axle. So we're going to use, I'm going to start here at the 1, like I have in the past. It's not very easy to see here. It's not focusing very well. But that is 1, 2, 3. It's 3/8 of an inch. Right, so the diameter of my axle is 3/8 of an inch. Now I put the knob back on. Okay, that's my wheel. So the wheel, I was using my effort here. So let's find our diameter of our wheel by just using the actual raised area. Okay, let's see if I can get a good look at this. Okay, and that is 1 5/8 of an inch. Okay, so 1 5/8 of an inch. So now I can find, by using those diameters, I can find my ideal mechanical advantage. Okay, so IMA equals DE over DR, which equals 1 5/8 over 3/8 of an inch. I'm going to simplify that to 1.625 inch over 0.375 inches. My inches are going to cancel out, and that equals 4.33. So my ideal mechanical advantage is 4.33. So now it's your turn to go to the lab and build the example of the wheel and axle.